The first of a sequence of demonstration scenarios that is covered by these recordings is addressing policy-based SON management. This demonstration scenario is also utilized to introduce the key components of the Semafour demonstrator. In the policy-based SON management scenario, we demonstrate how the integrated SON management layer performs an adaptive context-based configuration of a set of individually operating SON functions. This is done in a heterogeneous radio access network and in line with selected high-level network-oriented objectives. The high-level network-oriented objectives that are guiding the joint management operations of the policy-based SON management and SON coordination functions are formulated as a set of weighted key performance indicators with associated, possibly context-dependent, target values. Context in these scenarios is modeled by defining and distinguishing between cell classes, which are characterized by attributes that are of relevance to an operator when defining key performance indicator or KPI targets, for instance cell location, cell type, and the prevailing user mobility characteristics. The key objective of this demonstration scenario is to showcase the novel approach of instrumenting and managing a SON-enabled radio access network from the operator's perspective. It can be further observed how the SON functions are automatically reconfigured upon context changes, for instance when the network exits or enters the busy hour traffic load regime. Given the context-specific KPI target levels and adaptive SON function configuration, the scenario also shows the time-varying degree to which these target levels are met, or, in other words, to what extent the operator's high-level network-oriented objectives are achieved. The considered SON functions in this scenario are the LTE legacy functions of mobility robustness optimization and mobility load balancing, as well as the Semafour-developed LTE Wi-Fi traffic steering and high-mobility SON functions. While the demonstration is running, let us now first introduce the key components of the Semafour demonstration platform. The network panel shows a selected region of the operator's integrated multi-layer multi-rad network. The overall demonstration scenario covers an area of about 10 by 10 km in the city of Hanover, Germany, served by 195 LTE macrocells and 28 LTE microcells, all operating at the 1800 MHz band, and 28 Wi-Fi access points that are co-located with the LTE microcells and operate in the 2.4 GHz band. The area covers the city center, highways, as well as suburbs and lightly cultivated areas. In the GUI menu here, we find several options to configure what is displayed on the network panel. For example, we can choose to display a map with land use classes instead of the city map. Observe that the sector markers currently display cell loads using a temperature color scale from blue to red. See the legend here on the right. Note the distinction in display of the directional LTE macrocells and the omnidirectional collocated LTE microcells and Wi-Fi access points. The latter are depicted as concentric circles with the inner and outer disks corresponding with the LTE microcell and Wi-Fi access points respectively. As an alternative to the cell loads, we may for instance have the sector markers show the user throughput or cell class, a categorization of cells in a network that we will address later on. The GUI menu further allows us to configure attributes displayed for the user layer. The demonstration scenario includes a mix of users of the static, pedestrian, vehicular, railway, and highway types, initiating a variety of services such as voice telephony, video streaming, and file downloads. If we increase the demonstration speed on the time control panel, we will see how the degree of mobility differs across the user classes and how the vehicular users safely move on the roads of Hanover. If we right-click on a particular cell, we can read some cell-specific characteristics such as the cell ID, its radio access technology, and its frequency band. This further allows us to open a cell view panel for the selected cell. The cell view panel presents a local view of the network and shows detailed cell-specific information including key cell attributes, the current configuration parameters of SON functions if they are active in the cell, and the temporal evolution of selected KPIs and control parameters, a feature which we will revisit later on. Throughout the Semafour project, the developed solutions are assessed and demonstrated for selected regions within the Greater Hanover area, Germany, ensuring the consideration of realistic network topologies, propagation environments, traffic, and user mobility patterns. A subset of users, indicated with a white rim on the network panel, is prepared to be associated with one of up to 4 handheld devices that can be incorporated in the Semafour demonstrator. The handheld device will then show a video stream whose quality is emulated based on the time-varying performance experienced by the selected user in the demonstration scenario. This feature of the demonstrator enables us to give an impression of the user-level impact of the developed self-management solutions. In addition to the cell-specific KPIs shown on the cell view panel, the KPI panel shows the area-wide evolution of selected key performance indicators. For the policy-based SON management demonstration scenarios, the following cell class-specific KPIs are selected as most relevant, noting the concept of a cell class will be introduced shortly. The top chart shows the average degree of user satisfaction experienced in the different cells of the active cell classes, where for each individual call, a satisfaction between 0 and 1 is determined based on whether or to what extent the user's experienced throughput meets the requested data rate. The second chart shows the so-called short stay rate, expressing the number of cell dwell times observed per minute after a call handover that are shorter than 10 seconds. The third chart shows the cell class specific call drop rate, defined as the number of calls per minute that terminate prematurely due to either unacceptably low user throughput or due to radio link failures. The final chart shows the average resource efficiency, defined as the cell throughput in megabit per second divided by the cell load. The date and time are shown in the banners of the different panels, as well as more explicitly on the time control panel, indicating that we are currently observing handover in the morning of Thursday, October 8, 2015, the day this recording was made. The specific demonstration scenario is noted to cover a period from about 8 until 9 o'clock in the morning. The operator panel is the key interface for the network operator to provide input to and extract output from the self-management system. As this panel covers the most key aspects of the policy-based SON management scenario, we will discuss this panel in greater detail. On the Control tab of the Unified Self-Management System frame on the Operator panel, the different functionalities of the Unified Self-Management System may be switched on or off, including the Decision Support System, which can be activated here. Next, if the SON management layer is switched on, the operator is able to select one of the listed high-level network-oriented objectives, while he can furthermore activate or deactivate any of the listed functionalities at the SON management layer. In the current view, the selected objective is to optimize robustness, and both the policy-based SON management and the SON coordinator are selected. We note that functional activations or deactivations made in the Control tab are not effectuated in the network until the Deploy button is clicked. And, once deployed, the changes are effectuated overnight at times of relatively light traffic in order to minimize undesirable potential effects to ongoing traffic. For this reason, the self-management configuration that is currently active in the network is always indicated in boldface, which continues to apply until any deployed reconfigurations are effectuated overnight. Currently, none of the self-management functionalities are active in the network. On the Classes tab, we see a list of 34 predefined cell classes, which is a categorization of all cells in the network. The cell classes are defined based on the environment where a cell is deployed, the cell type, including the deployed radio access technology, the dominant mobility type occurring in the cell, and on whether the cell is currently operating in busy or normal hour traffic conditions. If we revisit the network panel for a brief moment, we observe that in the current GUI configuration, each sector marker indicates a cell class, using the same color codes as are used in the Cell Class Definition tab. On the Objectives tab, we can see how the high-level network-oriented objectives are formulated as a set of weighted key performance indicators with associated cell class-dependent target values. For example, for the Optimize Robustness objective, and considering for instance the cell class denoted Class 001 Normal, we note that the leftmost and hence deemed most important KPI is the resource efficiency, with the associated target set to keep this KPI above 40 megabits per second, while in order of relevance, further KPI targets are listed for the degree of satisfaction, the call drop rate, and the short stay rate respectively. A new high-level objective can be defined on the New tab. Back again on the Control tab, the operator can select which of the listed SON functions shall be active, provided of course that the SON layer is switched on, which it should be noted is mandatory if the SON management layer is activated. Note that, for instance, for the LTE Wi-Fi traffic steering SON function, multiple flavors exist, of which only one can be selected. The SON parameters frame on the operator panel lists for each of the SON functions the so-called SCV sets, or SON function configuration parameter value sets. Each such SCV set represents a dedicated configuration of the SON function. Just to give an example, we see that any SCV set for the mobility load balancing SON function comprises 5 configuration parameters whose settings are listed here. These parameters are to be understood as follows. If in a given cell the current load level exceeds the maximum load threshold, the load balancing function is triggered to take actions in order to offload traffic to neighboring cells. More concretely, these actions may entail explicit directed handovers as well as the adjustment of the handover offsets between the cell in question and one or more of its neighbors. It is noted that in case of an explicit handover, the handover offset between the involved cells is also adapted in order to ensure that the user stays in the target cell. Once the load balancing function manages to lower the load in the considered cell below the maximum load at source E0B threshold, no further load balancing actions are taken. When offloading traffic from the problem cell to a given neighbor cell is done, as mentioned by either explicit directed handovers or by adapting the handover offset associated with the cell pair, further such actions are barred once the load in the target cell exceeds the maximum load at target E0B threshold. The load balancing function will then attempt to shift load towards other cells. When adapting the cell pair specific handover offsets, the load balancing is restricted by the maximum offset it can select, given by the maximum cell individual offset parameter, and by the mandated step size in changing these offsets. In the policy and performance frame, the first 7 columns display a mapping of each of the defined cell classes to an applied SCV set per SON function. This so-called SON policy thus specifies how the SON functions for the different cell classes should be configured in line with the KPI targets set in the selected high-level network-oriented objective. By applying the SON policy, the policy-based SON management dynamically selects which of the available SCV sets should be applied depending on the time-varying and cell-specific context and the defined KPI targets. The SON policy is derived by the so-called SON Objective Manager function based on SON function models, which characterize the key workings of the different SON functions that are to be managed. As will be shown later, if the SON management layer is active in the network, the policy and performance frame continuously updates for each cell class how many cells are currently associated with that class, for each active SON function the SCV set that is currently assigned to that cell class, and the class satisfaction level, which indicates the extent to which the cell class specific performance targets are satisfied. 2 more frames need to be introduced on the operator panel before we address performance aspects of the policy-based SON management scenario. We note the log messages frame, which logs all SON or SON management decisions, and the decision support system frame, which generates a report each night to present the TSS findings. We will revisit the decision support system in detail later on. With both the SON management and the SON layer switched off, as is currently the case, we are now viewing the no SON demonstration scenario. In this scenario, none of the SON functions is active, and hence the network operates under fixed radio parameter settings, which serves as a reference scenario when assessing the performance gains from self-management. The temporal evolution of the selected cell class specific performance metrics experienced in this baseline scenario can be viewed from the KPI panel. One of the observations that can be made from these charts is the relatively high call drop rates, which can be improved by an effectuation of the SON and SON management functionalities, as we will show later on. Let us switch on the SON layer on the operator panel, but leave the SON management inactive for now. We accept the selected SON functions and click the Deploy button to apply this change. As mentioned before, any deployed changes are effectuated overnight. To avoid an unreasonable degree of patience from the demonstration audience, we fast forward to the next day by clicking the Next Day button on the time control panel. Observe from the date-time indication shown on the time control panel itself, as well as in the banner of the other panels, that we are in fact considering the same morning time slot but 1 day later. We note that the considered scenario on this next day in terms of traffic patterns and user mobility is statistically identical to that of the previous day, as it typically is on different days of a given work week. This allows a comparison between the performance effects of the different self-management configurations. As visible from the bold-faced text on the operator panel, the SON layer is indeed operational now, and the selected set of SON functions are active in the network. In the current demonstration scenario, a number of SON functions is activated with a fixed configuration, or more precisely, with fixed SON function configuration parameter value sets. The considered SON functions are mobility load balancing, mobility robustness optimization, multi-layer LTE Wi-Fi traffic steering, and the high mobility SON function. Since the SON management layer is still inactive, the SON functions are currently not dynamically configured by the policy-based SON management function, and potential conflicts between the functions are neither detected nor resolved by the SON coordinator. With the Semafour developed multi-layer LTE Wi-Fi traffic steering SON function considered in more detail in a separate demonstration scenario later on, let us now briefly address the workings of the high mobility SON function, as also developed within the Semafour project. The key objective of the high mobility SON function is to reduce so-called short stays. It does so by predicting the mobility behavior of currently active users based on measurements which were collected by users that were active in the past. Based on these predictions, the SON function aims at refraining from handovers that are directed towards cells in which a user is likely to stay for only a small amount of time, and at steering the user to the most suitable cell in the same or other cell layer or radio access technology, depending on its mobility behavior. To provide a deeper look into the workings of the high mobility SON function, let us open a cell view panel for this cell here and see how the SON function's trajectory identifier functionality has derived a set of reference trajectories from its measurements regarding typical mobility behavior in the cell's vicinity. Although not explicitly visible on the panel, it is then the trajectory classifier functionality which classifies active users by matching them with one of the reference trajectories. Based on the matches that are made by the trajectory classifier, the traffic steerer functionality then makes a decision whether and to which cell to steer users. Turning to the KPI panel, we first observe how the charts in the KPI panel indicate the jump forward to the next day with a new date stamp and a change of background color in the charts. From the charts, it can be observed that the performance of the displayed KPIs is indeed improved due to the optimization actions of the deactivated SON functions, compared to the no SON case, which applied on the previous day. The effect is most significant for the call drop rate, which is improved by about 20%. Although somewhat hard to observe from the shown curves, we note that the short stay rate is also improved by the traffic steering actions of the high mobility SON function. Let us now activate the SON management layer in addition to the already active SON layer, now including the policy-based SON management and SON coordination functions, where the latter is primarily involved in the detection and resolution of possible conflicts between the mobility load balancing and high mobility SON functions. We choose the Optimize Robustness objective, deploy the changes, and click the Next Day button on the time control panel in order to effectuate them. In the policy and performance frame on the operator panel, we now observe how the policy-based SON management function performs a cell class specific selection of the applied SEV set for each of the SON functions. If we click on a given SEV set, the associated SON function configuration parameters are automatically shown in a SON parameters frame. We now also see a time-varying class satisfaction in the policy and performance frame, showing the degree to which the class-specific KPI targets specified in the high-level objectives are met. As is clear from these figures, the joint operations of the policy-based SON management function and the underlying SON functions do indeed achieve a very high degree of cell class satisfaction, which is in line with the further improvement in key performance indicators that is displayed on the KPI panel. If we increase the demonstration speed to, for instance, 20 times real time, the changes in the cell class and the correspondingly assigned SEV sets are also clearly visible on the network panel, for instance when time evolves from normal to busy hour traffic conditions, or vice versa. At such times, depending on the GUI settings, we either see the cell class change or the applied SCV set for a selected SON function, both visualized in the colors of the cell markers. As noted before, alternative high-level objectives are supported in the demonstrator with corresponding effects on both the context-based configuration of the different SON functions and the induced performance effects. In order to keep the length of this demonstration within reasonable bounds, we will not get into these alternatives.